Welcome everyone to the webinar. We're so thrilled to have you join today. My name is Lindsay Snyder. I'm the marketing manager here at OCTOPUZ, and I'm going to walk everyone through some housekeeping items before I pass things off to John and our speakers, Rob, Alan, and Chris. So we'll have everyone muted throughout the presentation. Any questions you have, please type them in the chat box, and I'm just going to send out a welcome message so everyone knows where the chat box is. Rob, Alan, and John will address the questions at the end of the presentation. If for whatever reason we don't have time to answer them all, we'll definitely follow up with you one-on-one after. A question usually on everyone's mind is, will this session be recorded? Yes, the session's being recorded and it'll be in your inbox within 24 hours. So feel free to share it with your colleagues or follow up with any of us after. So without further ado, I'll kick things over to you, John.
Thank you, Lindsay. Hi, viewers. My name is John House, and I'm the head of sales here at OCTOPUZ. Today, I have the privilege to be joined by three talented individuals who will lead the conversations and demonstrations related to fixture design and offline robot programming. From Camtech, CEO Rob Thompson will lead the Nucleo demonstration portion, and prior to the demonstration, COO Alan Weeks will educate us on who Camtech is and what Nucleo does. My colleague Chris Height is an application engineering specialist at OCTOPUZ. Application engineers work with our customers on critical services that include training, implementations, and support. Chris will be running the OCTOPUZ demonstration today. Also on the webinar is Rob House, who will be keeping an eye out for questions in the chat box throughout. So we will spend most of our time demonstrating our respective softwares, but before that, we do have a brief presentation to talk about Nucleo, OCTOPUZ, and how we work together.
Thank you, John. This is Alan Weeks with Camtech. We represent the Nucleo weld fixture design software. The Nucleo weld fixture design software was developed specifically for the welding and fabrication industries. What Nucleo does is it provides a really easy to use and automated solution for creating inexpensive weld fixtures. These fixtures are formed from interlocking blades and base plates that are manufactured from flat sheet metal material. Many times this is just extra material that you might have laying around your shop. So this material can be used to create a weld fixture. And it really doesn't matter whether the part to be welded is in simple enclosure or an assembly of tubes or a family of similar parts. What Nucleo does is it drastically reduces the design time, the complexities associated with design, and also the costs that are typically associated with traditional weld fixture designs. Something else we also offer are the weld fixture design services for those customers that might not have the design resources in-house to do their own designs, or maybe they want to try out a Nucleo styled weld fixture to see how it works for their facility without having to actually purchase the Nucleo software.
OCTOPUZ is industry-leading offline robot programming software that enables robot functions to be programmed on a computer in a virtual cell that is an exact replica of your real-world robot cell, using built-in machine logic to identify the optimal paths or toolpath trajectory. OCTOPUZ programs the required code for a multitude of industrial tasks or applications and outputs the code in the specific language used by your robot brand. So while new jobs are being programmed, your robots can continue to stay operating, so there's limited disruption to productivity. Today, OCTOPUZ is a global team with representation in North America, Europe, and Asia, and we are hyper-focused on making the programming of industrial robots as easy as it can be.
So what problems do both Nucleo and OCTOPUZ solve? Well, regarding Nucleo, Nucleo is very fast, it's very easy to use. With the Nucleo software, you can produce a simple fixture really quick, and in some cases, 5 minutes or less. Software is very easy to learn. Typical training is 2 hours or less. When it comes to robotic welding, this is where you can really see an advantage using the Nucleo style fixtures over traditional style fixtures. And what Nucleo does, it helps make short-run, high-mix robotic welding more cost-effective and attractive to bid for. You can actually go after jobs that you typically would not be able to do due to the high cost associated with traditional weld fixtures. Then what everyone is concerned about is return on investment. Nucleo can definitely cut down on design time. It can reduce costs by utilizing low-cost sheet metal, as we discussed earlier, for manufacturing the fixture. Nucleo can provide enough savings to pay for itself within a short period of time. We actually have documented customer case studies of where they easily paid for the software after using it in just 1 quarter.
Thanks, Alan. On the OCTOPUZ side, historically, industrial robots have been programmed one of 2 ways, via teach-pendant programming or via the robot manufacturer's proprietary software. For more complex applications, both of these methods can be time-consuming and or difficult. We hear from prospects every single day that it takes them on average 1, 2, even 3 days to program their robot. So enter OCTOPUZ. For those customers who were programming by the teach pendant, we drastically reduced their robot downtime. For every second you are teaching the robot with the pendant, of course, the robot is not in production for you. And by programming offline through your PC, your robots can stay working for you while you are programming your next batch of jobs. This can be a massive driver for our customers. OCTOPUZ also drastically reduces the amount of time it takes to program. We consistently see 70 to 90% time savings over teach-pendant programming or OEM software programming. OCTOPUZ is an easy-to-use tool, it's sophisticated, and we program your part in minutes instead of days. Lastly, OCTOPUZ is agnostic, meaning we support all popular brands of robots. So instead of juggling multiple robot languages and OEM softwares, use OCTOPUZ as that single platform for all of your robot brands. So finally, how do Nucleo and OCTOPUZ work together? Why are we partners and why are we co-hosting this webinar? Simply put, in high-mix, low-volume robot production environments, there are often 2 bottlenecks. The first is fixture design, and the second is robot programming. Our mutual customers, that being Nucleo and OCTOPUZ, will import the CAD model of their part into Nucleo, design the optimal fixturing, and export G-code to cut and assemble the fixtures. You will then import that CAD fixturing into OCTOPUZ to create the robot program and output the code to load on to the real-world robot for production. So in a couple minutes here, you'll see that workflow by the 2 demonstrations that we'll present. So I think, Lindsay, that concludes the presentation portion here if we're ready to switch over to the demonstrations.
Yes, so we'll first be starting with a presentation and demo by Rob from the Nucleo team. So just bear with me as I get his demo environment set up. Okay. So Rob, you're able to take it away with your demo.
Hi everyone, I'm Rob Thompson. I'm the CEO of Camtech Software and the main developer of the Nucleo product. So let's go through how Nucleo works. In essence, with the software, you import the solid model. We support Parasolid and 3D IGIS as standard. We also have translators for other CAD systems. So you import the solid model of the weldment, and then in essence you go through and you follow the wizard. So the wizard lets you step through 18 steps. Each one you perform a certain task. So the first step really would be to orient the part correctly. So in this step you can rotate, translate, center the part over the datum, and then you can move on to the next step. You can set the part material, how thick are the blades, how thick are the base plate, so you can specify these values here. You can also set up a template, your favorite ways to do things. Next step is setting the bound, basically how much bigger the fixture is than the part. So if I go to a plan view, you can see these extend by default a little bigger than the part itself. So it's just a starting grid. This step is a base plate, so you can actually define the base plate, how much bigger than the part or the fixture blades it is. You can draw your own base plate, you can import a DXF of the base plate, and you can also use a weld table. It will actually place the fixture on top of the table, so you got a visual for where it's going to actually sit, you know, on the table when you come to use it in OCTOPUZ. You can also create what we call a parametric base plate, so you can reuse the base plate over and over again. There's a myriad of different options that we have here. On this page, we defined the boundaries that control the Z level of the fixture. So if you've got a kind of sweeping surface, you can draw boundaries to prevent the fixture going any higher than a given user-defined height. So if I turn the boundaries on, you can see there's a couple of flat boundaries that are defined for this this part, but you can make them, you know, a 3D shape, a swept surface, and move them up, move them down, tilt them, whatever you need to do. This step is if you wanted to do a grid of them, you want to do, say, 16, 4 rows, 4 columns, and a gap in X and a gap in Y. So you can do, you know, multiple parts of the same type in one fixture. You can also do, of course, dissimilar parts in the same fixture if you want as well. This step is the definition of where the blade lines are going, where these blades are going to be defined. So if I hide the fixture, you'll see that there's these purple and green lines which define where it's going to build upwards in Z. So I can move these, add them, I can stretch them, I can shrink them, I can step them around, I can snap them to user-defined positions like the center point of something or the midpoint. So you spend a little time getting this step done, but once you've done it, you know, you can always go back and refine it and change them around, add more, or shrink them or split them, whatever you need to do. Next step is the blade tabs that go in the base plate. So if I put the fixture back on, you'll see that underneath there's some little tabs that match the blades to the base plate. So you can define them to be just blinds like this that go in the thickness of the base plate, or you can make them a locking mechanism that means they go through the base plate and they then are shifted to the left, so they lock the purple blades to the base plate. So you can make a collapsible fixture. So you can define the size and width and depth of those in this dialog box. This is clamping, so you can import your favorite Destaco. In our case, we've got Destaco clamps, and you place them on the model and it will produce these towers to place the clamps on top of. So very simple to include clamps of your own. This step isn't often used, but it's managed torch access. You can basically put a solid model of the torch on there and see if it fits at a given position. It will do a collision check with the fixture when you build it. So say it will go red. It will tell you there's a collision between the fixture and the nozzle. This one we don't use very often, but if you draw the weld into the part, if we had a weld body around here and it had a naming convention we could use, we can pick it up and check to see if that weld is too close to the fixture, if it's going to possibly weld the fixture to the part. This step is the offset between the part and the fixture. So there will be some clearance between the part and fixture. As you can see, I'll repaint the screen. You see there's basically a small offset, which is around 20 thousandths of an inch around here. You can also put these bumps on the edge, which is good for boxes, where it will offset the fixture and at every inch or half inch it puts a 50 thousandths bump. And these are good for boxes and things with lots of surface area. You can file them down, gives you less friction, less heat transfer to pull the part out. So if the part isn't exactly the same as the 3D model, you can adjust the fixture. This is weight reduction. You can say I want to put holes in the fixture for ventilation, for access with the torch and weight. And you can do it on the base plate and also on the blades itself. Corner reliefs in the base plate slot. So it's these little Mickey Mouse ears that define some clearance in the corners, so you clean the curve from the laser out. This is pin towers, not used often, but you can select a feature in the fixture, in the part rather, and it will produce a little tower to poke up through that feature in the part. So it's like an alignment position. This is 16 of 18. This is the bolt holes. We could say we want them on the corners, we want them on the periphery, we want them all over the base plate. So your weld table bolt hole pitch can be put in here, or you can put them at user-defined positions, and it will put them wherever you need them. This step is colors, translucencies, and also the geometric things, tolerances, etc., which you can tweak if necessary. Then lastly, this is your part number, goes on the base plate, and then the annotation, so you know which one goes in which position. So very simple to put together, and then you're basically done. You then go off and build the fixture, and you end up with this fixture here. That'll take a few minutes. I won't start that now, but you end up with this fixture here, and you then can export it to CAD. So I can export it to CAD. So now it's going to export all the pieces as DXFs, create me a model I can take into OCTOPUZ, and complete the process. We do have options to direct edit this. You can lay it down as a sketch like you're seeing on the screen here, and put features or add changes to the periphery of the fixture blade. There's all sorts of direct editing you can do. But in the end, it produces the DXFs, Parasolid, STL file, which is a 3D printed triangulated file that you can look at on any Windows 10 PC without a CAD system to get an idea of what the fixture looks like. Okay, so it makes me a folder with all the files in, each individual file, and as I say, an STL as well of the part and fixture. So I go here, see here there's one you can bring in and look on Windows 10. But also, again, it will bring the STL, the XT file, the Parasolid will be brought into OCTOPUZ and used from there. We have a bill of material, how much material we used, how many pieces of the same, area perimeter, etc., squared area, and how many pieces, and the estimated weight of the fixture. So that's really the process. Very simple, follow the wizard, build the part, tweak the part, rebuild it, export the file. If you have any questions at the end, please feel free to ask. Thank you.
Okay, wonderful. Thank you so much, Rob, for taking us through that great demonstration of how to set up a fixture in Nucleo's software and the capabilities that you have. So now we're going to pass things over to Chris Height on the OCTOPUZ team. He will basically be taking this fixture in part, putting in the OCTOPUZ environment, and then programming it with Weld. So just bear with me as I switch over to Chris so he can start demonstrating. Okay, Chris, giving you access so you can start your demo.
So once you've created the fixturing for your part in Nucleo, you can import that fixturing and the part directly here into OCTOPUZ. So here I've got a fixture on that pressure vessel that we just saw. This one is for a little bit later on in the process. So we'll create some welds on this part right here. So I'm going to start by clicking on our Create Path button here in the top ribbon. And that's going to open up our path creation menu here on the right-hand side of the screen. And so the first thing I need to do is decide where my first weld is going to be located. And we'll start on this feature that we see right here. So I'm going to use my Edge and Curve tool and select the edge on the CAD model where I'd like to create a weld path. And it'll generate that weld path for me right along that edge. Just like that. So the location looks good. We just need to make a few more adjustments to it. So for starters, I'm going to change the starting position. It started where I had clicked, so I'm going to bring that more, I think, towards the kind of the 12 o'clock position here. That's starting to look good. If I wanted to make any other kind of fine-tuned adjustments to the location, I could do that as well. So, for example, if I wanted to restrict things to use only linear motions instead of the circle motions that it's using here, that's just a simple checkbox, and it kind of makes that change for me right away. Any kind of offsets, maybe from the two surfaces you're welding or additional wire stick out, you can see I can just incrementally change this. And our tool preview is going to change. The preview of our path is going to change as we make those changes to let us know what the new path will look like. Same idea for making changes to the tool orientation throughout the path. So if I wanted to kind of change my tilt, let's say, and tilt this in a little bit more, I can do that. Or if I wanted to add any kind of push or pull on the weld, these are all very easy things to make changes to here in OCTOPUZ. Once you have your sort of your welding path itself laid down, then we can start changing the more advanced configuration options of this path. So the first thing I want to change, for example, are the air moves leading into and out of the path. I'll just go ahead and jump into my leads menu right here. And so we can change everything we want to about these air moves. We can change the number of points, the direction of the points, the distance, the speed, anything like that. So for starters, for example, I'll just reduce the distance on the first and the last point here to bring them a little bit lower down, make them a little bit shorter, so there's just less air time. We'll kind of reduce the cycle time as best as possible here. So that looks good. Of course, with all the different options that you can change here, you know, that does come with quite a few settings you don't want to need to have to confront every single time you create a path. So what I can do is save a template of these settings, which I'll just call my leads like that, and hit save. And so in the future, when I'm creating more paths, rather than having to go into this menu at all and set any of these settings, just out here in the main menu, I can select those that template of settings right away. So, you know, if this is the default air moves that we see up here, I can go ahead and select that My Leads template, and it's going to make those changes for me and change those air moves for me right away. So it makes creating more subsequent paths quite a bit faster and quite a bit easier. And we can actually make use of these templates not just on leads motions, but also with things like stitch welding parameters or multi-pass welding parameters, or for the entire path altogether with all of its different settings. Maybe the one last thing I'm going to change here is I'm going to change it so that my tool is not you know, twisting and wrapping that J6 as much throughout the path. I'm going to have it try and maintain that same kind of twist the entire time, like that. So the last setting before I go ahead and create this is to set what the external axes are doing throughout the path. In this case, we just have one to consider. We've just got the headstock, tailstock. That's holding kind of the spine and the fixed string and the part. So I'm going to tell this headstock, tailstock to move and use coordinated motion as it sees fit and as it needs throughout the path in order to achieve kind of a 1F welding position as best as possible throughout that path. So we're going to have the torch pointing directly downwards and the weld bead kind of cradled upwards the entire time as best as we can. So we'll go ahead and hit create on that, and that's going to create that path. So we haven't gone in and solved any errors yet, but at first glance, we do have a collision that needs to be addressed, but overall things are looking not bad. So let's go ahead and address that error, the errors in this program right now. I'll start by running my analyzing tool. The analyzer is going to look through and you know, look for any kind of errors. It's going to look for collisions. It's going to look for joint limits, singularities, unreachable positions, things like that. And it is letting us know that we do have 3 points that are in collision. It's also highlighted for us exactly which points are in collision, so we can go and take a closer look if we'd like. But before I do anything, I'm going to get the solver to try and fix this for me automatically. You know, I could touch these up one by one, but I think the most efficient choice would be to get the software to just make these errors go away on its own. So I'll run my solver. The solver is going to go through. It's going to try to fix these for us automatically. And there it is. It has fixed those errors. So if I close this and we now take a look at that pass, you can see that it's adjusted the tool orientation as needed, and those errors are gone. So let's take a look at another weld over here. I'm going to just bring my robot up to this position right there, and we'll spin our rotary axis. Like that. And then let's zoom in underneath to this weld under here that we want to create along this cap on the pressure vessel. So I'll click on create, and we'll use that edge and curve tool again. Select this edge here. So I'll select that edge, and you can see there the path that it wants to create for me. It's automatically trying to flare itself out of collision, but I can actually overwrite that if I'd like. Maybe I want to force it to use a different amount of flare to avoid collisions here. I can go ahead and put in my own values as I see fit. So I'm really kind of pushing it to make it visible and easy to see. Of course, I need to change my air moves because this is not going to work. These air moves need to be different. So let's jump into that leads menu. I'm going to change things around so that my kind of coming into the path, we're going to come along the direction of that path. I'm going to also reduce the number of points. We don't need as many points in there in this case. And then for the end here, I'm going to have it pull back more this way. Again, I'll reduce the number of points. That's looking good. Again, once I'm happy with the preview I'm seeing, I can go ahead and hit create. It'll generate that path for me. So we've got a bit of a tight fit here between the fixture and the part and everything like that. And we can see that we have some sort of joint limits and unreachable errors that need to be resolved. So I'll just jump right ahead and run the solver. We'll run the solver specifically on this kind of statement that we just created really quickly. And there it's fixed that path for us as well. And so now that we've created this path, let's say I want to create the same thing on the other side of the part. I could go ahead and use kind of the same settings and sort of produce that again from scratch, but I think it would be more efficient for me to take the path that we've created here and actually just copy it over to this side. So I'm going to select that path and go transform. And I'm going to mirror it. I'm going to mirror it from this side of the part here on that cap over to this side of the part over here. So there's a preview of where that new path is going to be located. So I'm going to go ahead and hit transform there. That's going to copy that path over. So again, let's run this solver and see if we've kind of introduced any kind of new errors here, because of course, as we've copied it from one side to the other, the fixture is going to be different on that side. So we need to account for maybe the changes to the fixture. And so we do have a few points that we need to just quickly address. It looks like it's just at the end of the weld here. Things need to be tilted ever so slightly more. So I can go ahead and just quickly manually address these if needed. And then from here, we can go ahead and add any more air moves that we might want or need. So in this case, I've got these two air moves actually that I had created just a moment ago that I forgot to reorder. So start by taking these two and just clicking and dragging them into the right location before that second path. Drag those into place. And then we want to create some moves after the second path. So I'll start by pulling it up and away from that path. Let me just adjust the orientation here to avoid that collision. Let's go ahead and pull that further up. I'll put a move there. I'll do another one there. And then let's unwind this headstock, tailstock axis to get it ready for the sort of the next path that's coming up, that third path. So I'll put in that 180 and unwind it with an air move there. And we'll create some moves leading into our third and final path over on this side. So for starters, just sort of like a simple linear motion here for the beginning of that path. And before that linear motion, actually, I'm going to also create a point-to-point motion up above over here, like that. Perfect. So now that I've added a few air moves, let's go ahead and run our solver again on the entire program. We want to check everything, not just any individual path. We want to check also between paths and between air moves and things like that. So that's going to quickly check that. And you can see we are now 100% solved. So we could reset and simulate this. So now the final step is to post the code out to the robot itself. So I'll select my robot and hit the code button up here in the top ribbon. That'll open a File Explorer. So I'll navigate to wherever I want to save the file. I will name it, in this case, maybe just welding program or something like that. And you'll notice it's prompting me already to write it out as a .jbi file, a job file for a Motor Manual Scala robot using a DX controller. So this just highlights that the process for programming is the exact same regardless of which brand, model of robot you're using. It's only now at the end that it's going to determine the post files you need. So I'll go ahead and save that, and then we should see this code pop up. Yep. So this is the program that we just created in OCTOPUZ, written out as a job file for a Motorman robot. So I could put this on a USB stick, plug it into the back of my Motorman robot's controller, and go ahead and run that program. Of course, we're happy to take any questions you might have at the end. Thank you.
One for joining. Again, check in your inbox within the next 24 hours. You'll get this recording that you can share with your colleagues. And like Alan and John said, if you have any questions for either team, feel free to reach out. They'd be happy to help. So thanks again, everyone, for joining, and have a great rest of your day.